Welcome, welcome, welcome. Pull up a hard hat and take a seat, metaphorically speaking, because if you're actually near a pile driving site without a hard hat, we need to have a very different conversation first. Today we are diving, quite literally, into the ground. Specifically, into the fascinating, occasionally terrifying, and absolutely critical world of pile driving dynamics. Now, I know what some of you are thinking. Pile driving? That's just hitting things really hard, right? And to that I say, yes, but, and this is a very load-bearing but, it's about hitting things with exactly the right weight, at exactly the right speed, with exactly the right equipment. Otherwise, you're not building foundations, you're just making very expensive rubble. By the end of this course, you'll understand the physics, master the equipment pairings, and avoid the kind of field decisions that make structural engineers cry into their coffee. Let's get started. Let me paint you a picture. Imagine you're trying to drive a nail into a piece of hardwood, but instead of a hammer, you grab a feather duster. You swing it with confidence. Nothing happens. You swing it again, this time with feeling. Still nothing. Eventually, you give up, go buy a bigger feather duster, and wonder why the nail isn't moving. That, my friends, is what mismatched pile driving equipment looks like on a construction site, just with stakes that are, about 1,000,000 times higher. When hammer and pile are mismatched, three very predictable and very costly things happen. First, project delays, because inefficient energy transfer means the pile moves like it's filing taxes, slowly and painfully. Second, equipment damage, because high impact velocities and pile rebound will beat up both your hammer and your pile. Nobody wins. And third, safety risks, because dangerous tensile stresses and unpredictable rebound create hazardous site conditions. Concrete, as you can see from the cracked pile on screen, is not forgiving when it's unhappy. The relationship between your hammer and your pile isn't just a detail. It's the detail. Get it wrong, and the site will let you know in the most inconvenient way possible. All right, here's where we get to the actual science. Don't worry, I'll keep it accessible. I promise there are no differential equations hiding behind this slide. Probably. The single most important concept in pile driving is the ram to pile weight ratio, written as WAR to WP. The WAR is the weight of the ram. That's the heavy object in the hammer that does the actual striking. The WP is the weight of the pile you're trying to drive into the ground. Think of it like this. If you've ever tried to stop a shopping cart by standing in front of it, you know that a heavy, fast cart is much harder to stop than a light one. The cart transfers its energy to you whether you like it or not. In pile driving, we want that energy transfer. We want it controlled, efficient, and directed straight down into the earth. The transfer of energy from the ram to the pile is a direct function of their relative weights. This ratio dictates everything: your efficiency, your safety, and ultimately whether this project gets completed on time and on budget, or becomes a case study in what not to do. Master this ratio. It is your foundation. Pun absolutely intended. Now, engineers love numbers, but they also appreciate a good traffic light system because even the most brilliant geotechnical mind sometimes just needs to know, am I in the green zone or am I headed for trouble? So here's your color-coded field guide to pile driving performance. Think of it as the world's most consequential Yelp rating. Green, a 1-to-1 ratio. This is your 5-star review. This is chef's kiss. Maximum efficiency, maximum energy transfer, minimum drama. This is where you want to live. Yellow, a 1-to-2 ratio. This is pretty good. This is the solid 4-star restaurant that you return to. Acceptable performance for most standard driving conditions. You won't be thrilled, but you won't be filing insurance claims either. Red, a 1-to-4 ratio. Do not go here. This is the 0-star review where someone found something unspeakable in the soup. Inefficient, dangerous, and a recipe for bouncing hammers, cracked piles, and a very bad day on site. Keep this framework in your head. When you're in the field and making quick decisions, this mental model could save you time, money, and someone's safety. Let's talk about perfection. In construction, that's a rare word. Budgets are never perfect. Schedules are rarely perfect. The weather is famously imperfect. But a 1-to-1 ram-to-pile weight ratio? That, my friends, is as close to perfect as pile driving gets. When the ram weighs the same as the pile, something beautiful happens. Physics, for once, cooperates with us. The energy from that falling ram transfers into the pile with minimal loss. It's like a perfectly executed billiard shot. All the energy goes exactly where you want it. The result? You are highly efficient. Maximum energy drives the pile with minimal waste. Every strike counts. And you are safe. Good energy transfer minimizes dangerous tensile stresses in the pile, which means less risk of cracks, fractures, or that heart-sinking sound of a pile head giving up on life. As you can see in the diagram, the impact energy flows straight down as driving energy, with just a tiny loss at the interface. That's what you're aiming for, every single time. If there's one number from this entire course that you tattoo on your brain, and I mean that metaphorically, please don't actually, it's 1-to-1. Now, I know what you're thinking. You just told me 1-to-1 is perfect, so why are we even talking about 1-to-2? Excellent question, and here's your real-world answer. Because sometimes perfection isn't available, and really good will get the job done. A 1-to-2 ratio, where the ram weighs half as much as the pile, is the industry standard, and it's earned that status for a reason. In most conditions, it works. It's considered sufficient and effective for standard driving situations. Look at the diagram. Yes, there's more energy loss than the 1-to-1 scenario. That gray arrow is a little bigger, the driving energy arrow a little shorter. But energy is still getting down into that pile, and it's still doing its job. Think of it like a slightly inefficient car engine. You don't get 100% of the fuel converted to motion. Some of it becomes heat, some of it gets lost. But you're still driving, you're still moving, you're still making progress. The 1-to-2 ratio is the Toyota Camry of pile driving ratios. Not the flashiest, not the most exciting, but deeply, dependably reliable. And in construction, reliable is a compliment. We have now arrived at the part of the course where I must put on my serious face. That's right, no more jokes. For the next 2 minutes, I need you to look at those big red arrows on screen and let them burn into your memory. A 1-to-4 ratio, where the ram is just 1/4 the weight of the pile, is, and I quote from the field notes of every experienced engineer who has seen it in action, a mess. Here's what happens. The light ram hits the heavy pile. The pile, being much heavier, acts essentially as an anvil. And what happens to a ball when you throw it at an anvil? It bounces back. Hard. Your hammer recoils with tremendous energy, energy that was supposed to go downward into the soil, and instead it goes flying back up as rebound. Wasted energy, safety hazard, chaos. To compensate, operators often crank up the impact velocity. More speed, more power. Unfortunately, this just means a very fast, very damaging blow that still doesn't drive the pile efficiently, but now has enough energy to crack the pile head-on the way out. This is the turning it up to 11 on a broken amplifier of pile driving decisions. Loud, damaging, completely counterproductive. Avoid the 1-to-4 ratio the same way you'd avoid an unfenced excavation. With respect, with urgency, and without exception. Now that we've established the theory, the beautiful, elegant, ratio-governed theory, it's time to get our boots muddy. Theoretically. Here's the thing about the ideal WR to WP ratio. It's not a universal constant that you just slap onto every job site and call it a day. What the ideal looks like in practice depends entirely on what you're trying to drive into the ground. Different pile materials have different characteristics. They behave differently under impact. They have different tolerances for stress, for impact velocity, for the type of hammer you use. And if you ignore those differences, the pile will remind you of them. usually in the form of cracks, failure, delays, or all three simultaneously. Over the next few slides, we'll look at four major pile types: concrete, steel H-beams, sheet piles, and timber. For each one, I'll give you the key characteristics, the recommended hammer type, and the target weight ratio. By the time we're done, you'll be able to look at a pile spec sheet and immediately know what equipment setup it calls for. This is where the knowledge becomes actionable. This is where you go from understanding physics to actually using it. Let's go. Concrete piles. Strong, heavy, capable of carrying enormous loads, and about as forgiving of a bad hammer match as a brick wall is forgiving of a forehead. The key characteristics here are high mass and brittle nature. Concrete can handle enormous compressive forces. That's why we use it. But hit it wrong, and those dangerous tensile stresses we talked about earlier will crack it right open. You saw the photo in slide 2. Not pretty. Very expensive. Very avoidable. For concrete piles, you want a hydraulic or single-acting diesel hammer. These give you controlled, powerful, consistent energy delivery. And critically, you want that 1-to-1 weight ratio. The heavy ram matches the heavy pile. Energy transfers cleanly downward. The concrete compresses. The pile advances. Everyone goes home happy. The key takeaway? A heavy ram is essential. The 1-to-1 ratio isn't just recommended here, it's critical. Without it, you risk fracturing the pile from excessive impact velocity, which means you've just destroyed the very foundation you were building. Concrete piles are not the place to cut corners on equipment selection. They will not give you a second chance. Steel, the tough kid on the block. Durable, high tensile strength, and compared to concrete, practically forgiving. Practically. Steel H-beam piles are lighter than their concrete cousins, which changes the dynamic somewhat. They can absorb a good deal of impact without shattering. Steel bends before it breaks, which makes it more resilient. This is why we can comfortably operate at a 1-to-2 weight ratio for steel H-beams rather than demanding the stricter 1-to-1 of concrete. For hammer type, you'll typically deploy a diesel or vibratory hammer. Diesel gives you powerful impact for harder soil conditions. Vibratory hammers work well in cohesionless soils where you can literally vibrate the pile into place, which frankly sounds much more civilized than just pounding it repeatedly. The 1-to-2 ratio for steel H-beams provides what the document calls a balance of efficiency and practicality. And that balance is real. You're getting good energy transfer, you're not damaging the pile, and you have practical flexibility on equipment. Think of steel H-beams as the cooperative colleague on your project team. They'll work with most reasonable approaches, as long as you treat them with respect. Now, sheet piles are a little different, and I want you to pay attention here because this one surprises people. Sheet piles are interlocking sections driven into the ground to form a continuous wall. Think retaining walls, waterfront barriers, excavation support. They're long, they're thin, and they are driven in a completely different way than the other pile types we've discussed. Sheet piles are driven by vibration, not by impact. That changes everything. Because we're not slamming a ram down onto them, the whole concept of the ram-to-pile weight ratio simply doesn't apply. You'll notice the weight ratio on screen says N-ln A, and that's not a typo, that's the physics. For sheet piles, you use a vibratory hammer. And instead of worrying about WR to WP, the critical metric becomes the eccentric moment. Essentially, the measurement of how much vibrating force the hammer generates. Get the eccentric moment right for the soil conditions, and the pile will practically walk itself into the ground. The lesson here is an important one. Not every problem uses the same tool. In construction management, knowing when a principle applies and when it doesn't is just as important as knowing the principle itself. And finally, we come to timber piles, the oldest pile material in human history. Ancient civilizations built on timber piles. Venice, Italy sits on millions of them, still standing after centuries. So let's give timber the respect it deserves, and then talk about how to not destroy it with a bad hammer choice. Timber is a natural material. It's strong in compression, reasonably resilient, But it has a critical weakness: overdriving. Hit a timber pile too hard, too fast, with too much energy, and you'll cause what engineers charmingly call brooming, where the top of the pile frays and splinters apart like a broom. It's as bad as it sounds. It's basically destroying your pile from the top down. For timber piles, you use a drop or air hammer, and the governing principle is this: control over power. You are not trying to maximize energy, you are trying to minimize damage. Low, consistent, carefully monitored energy per blow. There is no ideal WR to WP ratio listed here, because the focus isn't on optimizing energy transfer. It's on selecting a hammer with adjustable and relatively low energy output, and using it carefully. Timber is patient. Timber is ancient. Timber will reward a careful hand with centuries of reliable service. And it will absolutely split into matchsticks if you treat it like a concrete pile. Respect the wood. All right, take a breath. Let's zoom out and make sure the big picture is crystal clear. Everything we've covered today distills into 3 governing principles. 3 things. That's it. If you remember nothing else from this lecture, remember these. Principle 1. The why. Mismatched equipment is a direct path to inefficiency, cost overruns, and safety failures. There is no scenario where getting this wrong is acceptable. Every hammer pile mismatch has a cost, and that cost is always paid on site. Principle 2. The what. The ram to pile weight ratio, WR to WP, is the single most critical factor in driving dynamics. A 1-to-1 ratio is the benchmark for peak performance. This number is your North Star. Principle 3. The how. The optimal ratio and hammer type are dictated by the pile material, not by what equipment happens to be available, not by what's cheapest, not by what worked on the last job site, by the pile material. Match the equipment to the specific application every single time. These 3 principles work together. Understand why it matters. Know what controls performance. Apply the how to every project you manage. That's the system. That's the framework. That's how foundations get built right. And here we are, the final slide. The image on screen, that beautiful bridge lit in the golden light of what I like to think is a successful project completion, is a reminder of what all of this leads to. Real infrastructure, real safety, real results. The tagline on this slide says it all. Master the ratio, control the impact, deliver the project. 3 sentences, 3 actions. A career's worth of discipline behind each one. Precision in planning prevents failure in the field. That phrase should be on a coffee mug on every construction manager's desk. Because every decision you make in the office, in the planning phase, in the equipment selection meeting, it ripples out to every strike of that hammer, every meter of pile driven, every structure that eventually stands on those foundations. The people who will cross that bridge don't know your name. They won't know what equipment you specified or what ratios you calculated. But they are counting on you right now to get it right. So get it right.